but I think the story works.
9年開始とか骨瓶
The challenge is to stay awake after lunch.
你现在手机号码多少？
I always like having the class in the morning because then people have not fallen asleep after lunch. There's not enough board space, of course, here, but we do the best we can. And is there an eraser that works? It sort of works. All right. So let us continue our discussion. I think it's as a matter of basic material. Today I'm going to continue with this board doesn't drive me crazy. Continue with drift waves. Basically waves and instabilities. Talk about sort of the simple basic physics. So this is not really about turbulence theory. So we're slipping one lecture, and then tomorrow we will talk about wave turbulence. So I think some of you are expecting wave turbulence today. It's important to talk about the basics. All right? So anyway, you may remember last time we talked about basic models. And we derived two of these, I think, fundamental models, and I just write in normalized variables. The Hasegawa-Wakatani model for collisional drift waves. Right. And it's understood that this is phi hat, right? Everybody knows is E phi over T. And N hat, I'm going to stop writing, is N tilde over N naught, and all this good stuff. And this is the vorticity equation, and then we have d by dt of N hat plus what amounts to d star dy phi hat is equal to minus d parallel del parallel squared of phi minus n, right? And in the limit, and this is the kind of fundamental model, it is rather restricted, but still quite useful. And we'll talk about kinetic theory today too, though. And then in the limit, I mean the very relevant limit of k parallel squared d parallel over omega larger than 1, which is the Boltzmann or adiabatic limit, we get our beloved friend the Hasegawa-Mina system. And I mean, and if I wanted to be technically correct, I could add a viscosity here, and I could add a residual kind of collisional diffusivity here, and the same thing here. By the way, a good exercise, chatting with a few of you yesterday, a good exercise is to derive this. Nobody knows. Okay. Why don't you leave the door open so or unlocked or whatever, so whoever wants to come in can come in. So this is, I think, requires you to work through the basic derivation, starting from the basically working with the polarization drift. So what basically to do this, what you have to do is retain the viscosity in calculating the net polarization flow. It's a good little exercise to make sure you know what's going on. I discovered there was some confusion about that. A couple of you asked some good questions. And basically the reason, one of the critical issues in fusion, as we discussed the first day, is confinement. And, really the central question in confinement is driven by, what are the consequences of drift and ITG, and I'll talk a little bit about ITG today, instability. But they're all kind of, they're like debating the difference between lions and tigers and jaguars. They can all kill you very easily, okay? So I think it's better to study one species in depth. So then we looked at the question of then collisional drift wave instabilities. This is where we were closing before. And you remember that the instability is tied, of course, to the non-adiabatic part of the electron density. So in other words, we write the total N as the Boltzmann piece plus the non-adiabatic or non-Boltzmann piece. And we solved for the non-adiabatic part as, I believe, minus omega star. Where this is the diamagnetic frequency, and then there was omega plus I k parallel squared d parallel times E phi over t, right? And then after a bit of arithmetic, we showed that, basically that what I would call delta omega k over omega k0, and omega k0 is just, the usual Boltzmann electron limit drift frequency, 1 plus k perp squared rho s squared in the denominator, is equal, basically scales as omega k over k parallel squared d parallel times what amounts to 1 minus, do I have all my pieces right here? 1 minus omega k over omega star. And maybe it's a little more illuminating to write it as omega star over omega minus omega star. Now, remember, this is basically where we were yesterday. Now, this is worth a lot of discussion, and I think we kind of, and there was the party on Tuesday or something, so. Crucial to the instability. There's two things, okay? There are a couple of, first of all, what kind of instability is this? This is an inverse dissipation process, okay? And, Dr. Zhu here was raising some good questions that I'll answer as we go along here. What is this, right? This thing is dissipation. And this is where the inverse comes from, right? Yeah. The inverse really comes from the fact that omega has to be less than omega star, right? So basically, you need some damping plus omega less than omega star. A good example, can you think of a simple a simple problem in that I gather you all study one-dimensional plasma waves and instabilities. Can you think of a simple kind of familiar one-dimensional instability that fits this paradigm? The current-driven ion acoustic. Well, I'll mention that later, but I think my impression is you guys all know that one. And you recall, what you need for that is you need electron Landau damping. So there's your dissipation. This might be a good one to review if if you haven't read about it in recent history. And you also need what amounts to basically the analog of omega minus omega star becomes in that problem omega minus kV drift. And since it's an ion acoustic wave, you need, right, omega is of course KCS. So as you all know, you need V drift bigger than the speed of sound, right? But in some sense, V drift bigger than the speed of sound is very closely analogous to omega less than omega star in the drift wave problem, right? So I would recommend that as a homework problem, maybe make this connection. And this is, I think, a good one to try. All right? You guys all study the current-driven ion acoustic, right? That's a classic one-dimensional plasma instability that you all learn, everybody learns in Plasma 101, right? Anyway, we can discuss that a little bit in kinetics, okay? Now, so what else is necessary to say here? So the question, I think a very fair question you might have, is how does the energetics work? I don't want to erase this equation. Let me just now. I can erase this. Okay, so do you guys believe this? If you were a skeptic, I mean, this should bother you. I think it was bothering you last time. You were kind of asking, I mean, a natural question that a student should ask is how does somehow dissipation get turned into instability, right? That's, and of course, this is the key point here. Right? And that is a very fair question that you should ask. And the stock answer is that dissipation basically allows a non-zero cross phase. So in other words, dissipation allows V radial and tilde to be non-zero, to go from 0 to positive. So it allows you to relax the density gradient, right? Remember, I mean, in this drift wave instability, in all instabilities, you should ask the following question. The underlying wave is the drift wave, right? The free energy source. The free energy source is grad N. It can also be the temperature gradient, and in some cases the parallel flow, right? And what I might call the trigger is the dissipation. Right? You should always kind of sort that out. That's a really very important things to keep track of. Okay, so now, what must be true? Let me ask you, if in fact this scenario of inverse dissipation really leads to instability. Right? There must, something in the basic energetics must be true. And you guys are supposed to be skeptical consumers, you know? So what's the critical question here? Well, somehow for this not to be a swindle, it had better be true that the energy liberated by grad N relaxation, right, had better, in some sense, had better be bigger than the energy dissipated by this parallel diffusion, right? Right? For growth of fluctuations from the equilibrium, from the free energy source, it had better be the case that you're gaining more from the relaxation of the density gradient, that's the free energy source in the problem, than you're paying in this, you know, small dissipation, or not necessarily small, but in this dissipation here that allows you to shift the cross phase, right? That's the critical question. So how would you answer that? You guys tell me. Well, you answer that by looking at the energetics of the fluctuations. Okay? That's right. So what you need to do is set up something like an energy balance relation, right? How would you set up an energy balance relation here? What are the two constituents in the energy? Again, if we're, think ion acoustic wave, right? Well, the answer is there's a kinetic energy associated with the fluid motion, and there's an internal energy, right, associated with the density perturbation, right? In unfortunately with the blackboards here, we have to erase, so. We're going to have a, speaking of, so what's the total, how would you write the energy density of the fluctuations? Right, well, the energy density in unnormalized variables would be something like rho naught V perp squared over 2, right? That would be the kinetic energy of the fluid motion. And you would also have something like an internal energy. You would have something like TE times n tilde over n, right, times n tilde. So it would be something like TE n tilde squared over n naught. And this would be, and there's a 2 there, and this would be internal energy. Right? Righty?
Yeah.
Right, because we have there is a thermal energy content in this. I mean, really, you know, omega star. I mean, V star. Right? Let's not forget. V star is equal to what? It's rho s CS over L sub n. So that goes as essentially the electron temperature over the density gradient scaling. So there is an internal energy content. The density gradient effectively, grad n effectively, grad radial n average effectively defines grad radial of the electron pressure, right? You want to think in terms of pressure. So there'd be something like that, wouldn't there? Right? Now, how would you derive an equation for something like that? Well, very simply, you realize if I profoundly write this as number 1 and number 2, right? So from the Hasegawa-Wakatani equations, right, and I'm gonna, since we haven't been talking in this simple limit in terms of diffusion and viscosity, I'm not gonna keep it here. Basically, what I would write is something, I would basically derive, something like this. I would multiply equation 1 by phi and integrate by parts, and then that would become the time derivative of the kinetic energy, wouldn't it? Right? So that would be, so I could play some game like this. I could write this as integral minus d cubed x, then phi, times d by dt of del squared phi, and then integrate by parts, don't worry about the boundary. And so this is equation 1. And likewise, I could write, again, in normalized variables, n times dn hat dt, right? And that's equation 2. And this one would do the sign in here, so. All right, this one we don't have to integrate by parts. Okay? And that would form an expression that is essentially analogous to this. Z perp, right, is nothing more than del perp phi squared, right? That's the kinetic energy in this system, right? So if we do that, that's just a little bit of arithmetic for you daring people.
When you say instability, you mean the growth of epsilon?
Excuse me?
When you say instability, you mean if the total energy grows?
Right, I mean, yeah, in other words, what I'm trying to do is I'm trying to calculate d by dt of the fluctuation energy, right? And I want to show that this is positive.
Okay.
And I want to show there's a certain inequality and there's a competition between terms that has to be positive, in other words. And that competition is related to omega minus omega star.
So what you mean is that the second term may decrease, but the total one will increase?
Well, the total has to be positive, so the
But the
sum
second-
of this and this has to be positive.
Yeah, but what you just said is that the second term might decrease.
Well, look.
Is that true? The second
Why don't
one-
you calm down for a second and then you'll see what I mean, okay? So how could we, in terms of this, you realize we can write n minus phi as equal to h, our non-adiabatic part, right? So then we do all this arithmetic, and we find okay, so we find that d by dt of, let me put it, integral grad phi squared, bracket, just with n plus n tilde squared bracket. So this is, right, the time rate of change of the total fluctuation energy is equal to now a sum of two terms, a dissipative part, integral d cubed x times d parallel times grad parallel h tilde quantity squared. And really the bracket includes, you know, everything, so I could, let me write this as an integral over radius, integral over x, and then I don't need the d3. So the bracket includes the y and z. So I have a negative term, and we have another term, which is minus integral dx v radial times n tilde, right, times dn naught dr over n naught. Okay? All right, now where did this come from, right? Pretty easy to see where this come from. Each of these things is just h, right? So what I do is, to form energy, I write this, I multiply this by phi. I put a phi here and integrate by parts. So I have a grad parallel phi times grad parallel h. Here I multiply by n. I put an n here and integrate by parts, and I have grad parallel n times this, okay? And then, of course, when I combine the two, how shall I say it? They combine, so I end up with grad parallel h squared, right? Because it becomes something like grad parallel phi, right? Right, and remember there's a sign flip, so there's something like grad parallel phi times grad parallel n, and n is equal to phi plus h. So when all is said and done, I get grad parallel h squared. Right? And similarly, this guy just comes from taking our friend n here, right, and multiplying through him by n and bringing him to the other side. So I have something like this, right? Right, so this is just particle flux. All right, that clear to everybody?
You integrate over the angle.
What?
You integrate over
The angles are in the bracket.
Yeah.
The bracket includes integral d theta over 2 pi, integral d phi over 2 pi, or if you like to work in the slab, dy dz. Okay? Right, so you notice you've got two terms here.
Excuse me,
Yeah.
I have some question.
Yeah.
What about the condition of that the energy is liberated, but the dissipation tends to 0? Is the instabilities will translate into turbulence?
No, well, you mean you're asking what happens if this goes to 0?
Yeah.
If this goes to 0, there's no linear instability. Okay?
No, I don't mean this. My meaning is that the epsilon partial t greater than 0, larger than 0, but the dissipation tends to 0.
Oh, oh no. I'm asking, this epsilon is just the fluctuation energy.
Yeah.
Okay, this is not, this is not the turbulent dissipation rate,
Yeah,
if that's
yeah.
what you're asking. This is just the fluctuation energy, all right? So we're not talking about cascades or anything like that. We're talking about kind of the linear instability, okay? So we're just asking what are the conditions for linear instability from the point of view of energetics? That's the question here. Very simple question. This is one that's clear. All right, so you can see the two players here, by the way. This guy, right, and by the way, I think it's immediate that I can write this now as h, because the only contribution to the particle flux is from the non-adiabatic part, right? So very clearly, this guy is negative definite, and this is damping, right? In other words, all other factors being irrelevant, this term will make a negative definite contribution to the rate of change of the fluctuation energy, right? It will damp things. This thing is clearly the free energy source, right? Right? And this thing is basically the relaxation. Right? This is the thermodynamic flux. Right? So clearly this thing has to be positive for instability, right? I think I can erase this now. All right, I think we need the space, so. All right, so very clearly, you know, fluctuation growth, d by dt of c being positive, clearly requires that we must have, you know, minus d parallel del parallel h quantity squared, right, plus, where's my friend, we have a minus sign there, and we have a minus sign there, minus v radial h times d1 naught dr, and then I take care of all the factors through. And I bring the n naught underneath, so this is n tilde over n, it's just that. So, let me put the n naught here. So this thing has to be positive, right? This is negative definite. Right? This is, you know, positive definite, right? Because ultimately this is outward flux. Okay, we'll in this simple model, what's an easy way to write this? We haven't derived it yet, but you should be able to guess. What's an easy way to approximately write this? If you did quasi-linear theory, what would the form be? It would be something like a diffusion, right? So this would be a minus, I'll show this, some turbulent diffusivity times dn dr. So the whole thing with the minus sign becomes a plus d turbulent dn dr squared. Right, so this is a classic kind of diffusive mixing source, right? It's driving the thing. So the interesting question, this is clearly positive if you have instability. And for consistency with instability, if we call this term 1 and term 2, this is negative, that's positive, so clearly the magnitude of 2 has to be greater than the magnitude of 1, right? That's what it comes down to. That's the condition for instability. Right? Now that is an interesting little question. There's the eraser. Everybody see that? That's a close race. It's closer than it looks. Okay? You guys are frowning. You should see that. This is effectively saying the condition that production, right, has to beat dissipation. But the problem, the subtlety is different from, say, Kolmogorov. Production is in some sense a function of dissipation, right?
Yeah.
Right? That's what makes this a little bit more entertaining, right? than simple Kolmogorov, right? So you have to show this is, you know, at least at the level of, you know, mean field theory, that this is satisfied. So what's the comparison? Well, what do? At the, you know, at term number one in terms of order of magnitude, you have a k parallel d, right, k parallel squared d parallel, and then you have an h tilde squared. And h tilde squared is omega minus omega star squared over k parallel d parallel, k parallel squared d parallel squared phi squared. Right, that's our friend term number one. Term number two, right, well, what's the attitude, you know, v radial times this thing. In terms of a frequency, you have v radial times this. This is going to be basically phi hat times omega star. And h is going to be omega minus omega star over k parallel square v parallel. So you notice you get some cancellation, and then you have another phi, so you have a phi squared. So this goes out and that's gone. So you notice you have, ultimately you have a very, very close horse race. If you look at the factors here, term number one, you know, if I don't worry about the phi squared, is omega minus omega star squared, right, over k parallel squared d. And term number two is omega minus omega star times omega star over k parallel squared d. So you see, it is absolutely essential for instability for omega to be less than omega star in order to have production to exceed dissipation. Okay? Critical result. And the energetic argument, I think, shows, in a sense, how subtle the drift wave instability actually is. Okay? Right? You notice the difference. If you ask, what is the difference in between these two terms, it's one has an omega star, one has an omega minus omega star. That's the difference in the size. Right? And so in some sense that this condition is critical to the instability process.
Sorry, I cannot see that.
What?
I cannot see that from here. You mean that the second term should be like?
Well, suppose omega was, I'm saying for term number two to be bigger than term number one, you must have, you know, here you have omega star, and here you have an omega minus omega star, right? So I mean, look, I've squared, so I can write it as omega star minus omega squared. So in other words, in our convention, the frequencies are positive, so it's always the case that omega star is bigger than omega star minus omega, right, for drift waves.
Yeah.
Right? Because omega is just equal to omega k, which is equal to omega star over 1 plus k perp squared rho s squared. Right? So it's absolutely essential for the frequency to be less than omega star in order to have production to beat dissipation. And that is really the answer to your question of the last time, of yesterday, Tuesday. In some sense, this subtle interplay of dissipation and the instability process. And that's when I called it earlier, of course, with the board, it's erased, but an inverse dissipation process. Right, it's That's what the word inverse means, right? Omega less than omega star. So it's a kind of, as I say, it's really a case of that production is beating dissipation, but at the same time, production is a function of dissipation. That's what makes the drift instability a little subtle, okay? What do you think the dissipation process is in the collisionless limit? What replaces this parallel damping thing? Landau damping, of course, Landau resonance. We'll show that.
I think it's something like the Landau damping, inverse of the Landau damping.
Excuse me?
I think the dissipation is something like the Landau
Yes,
damping.
of course. In other words, here in the collisional drift wave, you have parallel diffusion. Right? In the collisionless drift wave, then you have kind of parallel resonance, which is Landau damping, which I will show today. So the two certainly are, yes, related. You know, in some sense, the parameter here that is of relevance is k parallel squared d parallel over omega. For the case of this thing, the relevant parameter is k parallel d thermal over omega, right? They're clearly kind of different ways of looking at fundamentally similar things.
I have a question.
Yeah.
The damping rate because the parallel diffusion, but when these coefficients become larger, the growth rate becomes
Growth rate
smaller.
goes down, exactly.
Yeah. So, I mean, this coefficient must be response for the rate of the instability, but
Right.
it seems it still can reduce the instability.
Yes, you're quite, I mean, because what happens? I mean, good question. What happens if I make k parallel squared d parallel over omega go up? What's happening there? What's the limit of this go to infinity? It's a good question. Right, the limit of, as this goes up, the ratio of the non-adiabatic part to the adiabatic part goes down, right? As this goes down, the growth rate has to go down, and also the flux of particles has to go down as well, right? So as you make this larger, you're making the electrons more and more like Boltzmann. In the limit of Boltzmann or adiabatic electrons, there's no instability. That's what's going on there. Okay? It tells you the maximum, the growth rate can never go above omega star, right? Or actually the wave frequency, because you're always, in a sense, if this parameter goes to infinity, becomes large, the growth rate goes as 1 over that. If this is small, less than 1, as you might guess, the growth rate is proportional to that. Okay? And think about it, right? The growth rate, what does the growth rate go as? It goes as essentially omega k times omega k over k parallel squared d parallel. This is in the limit of k parallel squared d parallel over omega bigger than 1, right? So this factor is always less than 1. good exercise is to work out the growth rate in the limit where this is small. That's usually not of relevance in current days, but, you know, what is gamma for k parallel squared d parallel over omega less than 1? Little homework problem for you. Okay? You just do a linear stability analysis in the other limit. But this is quite crucial, right? In other words, the essence of the instability is, again, that dissipation triggers production, and that production, though, is bigger than the losses due to dissipation. Really quite critical. That's why I call it an inverse resonance process. You won't find that little demonstration in any books, by the way. I've never seen that. I have to sort of work it out.
I'm sorry, do you have a more systematic way to show that? This is a kind of automatic, you have some coefficient for that.
Well, I'm saying at the, it's not order of magnitude. I mean, I'm saying at the level of linear theory, I can calculate all these exactly with linear response theory, okay? This calculation is about the linear growth rate. So I can calculate those things at the level of linear response theory rigorously. So that's what I did.
But what that means that when you estimate these terms,
Yeah.
you have some coefficient.
There's no coefficient. There's, at the level of the linear instability, there's no coefficient.
No, I mean, in the estimation of the second term, you have to estimate the flux term, right?
Yeah, so when I use the linear response for that, all right, I don't have to estimate anything. I can at the level of linear perturbations, I can calculate that exactly.
The diffusion coefficient, the R, what is that?
Right.
Should be 1?
Well, we're coming to that, okay?
Okay.
I mean, but I mean, at the look, I mean, there's nothing, where's the eraser? There's no swindles here at the level of linear theory.
Okay,
At the-
linear.
Right, you know,
Linear.
yeah, but
它那个什么意思啊？
we're asking the question, what is the essence of the energy production in the linear state? Okay, that was the question.
它这个减小，
Not turbulence.
What?
它这个跟它这个减小，
Yeah, exactly.
然后
But
最后
I
它还说
mean,
这个东西，
you know, ultimately, then you have to
他
ask,
说这个
in some
这个
sense,
减小，
you know, you have to think about this energy balance in the turbulent state, and that gets into these, you know, these games of rigorous bounds and all of that. But look, at the level,
那里第三项，
I was going to do
第二
that
项最
next.
小，别的就是你那个 H 减小了之后，它自然就这个，然后
Alright,
最后
so
导致
let
这个东
me
西那个
erase
一
this,
的绝对是小于2，
and erase this, and let me
它这
keep
东西
this.
它是冲出来的嘛？
I need the space.
它这个减小会导致这个减小吧？导致这个减小，然后这个减小之后它还会有1还小于2，就是2降的比1快，
Alright,
2是平方
so,
square。
alright, so the next question is how would you do the quasi-linear calculation of the flux? And this is related
就平方
to
不给它面。
then also your question of, you know, the CDT calculation for linear perturbation,
你是跟哪个老师？
for growth
啊？你跟哪
of
跟哪个老师？
perturbations.
听我，秦老师现在已经
All right, so you could ask two questions. I mean, you could ask, you know, how would you estimate the flux?
今年是1年级，几年级？
Right? And you could ask, how would I, at the level of linear theory, how would I calculate this? So this brings us to doing quasi-linear theory. And I agree that quasi-linear theory is limited, but I think it's better to understand it well in order to understand its limitations. It often works remarkably well. Okay, so how would you do a quasi-linear calculation of the flux? Right, if you were trapped on a desert island and they asked you, we gotta design, we gotta come up with a transport coefficient heater, how would you estimate it? You guys, well now Professor Wong told me you guys all had quasi-linear theory. So how would you estimate that? Silence reigns. I think it's very, this is I think it's very important to go through these fundamental little exercises, right? And you realize this is just a particle flux, right? This is effect by definition is equal to this.
This is Vlasov equation.
What?
Vlasov equation.
Okay, but do we need the Vlasov equation here?
One moment of Vlasov equation.
What?
One moment of Vlasov equation.
Yeah, but I mean, what would you do? You just stick in the response of H here, right? I mean, you just basically here, you would say at the 0th order, simple thing to do is I would calculate basically, the linear response of H to phi. Right, and I would just stick that in. And this we remember we calculated as H is equal to minus omega star over, what was it, essentially omega plus I k parallel squared d parallel times phi, right? We'll just stick that in there. That's quasi-linear theory, sticking in the linear response with the condition that the frequencies are now equal to the linear eigenfrequencies. So you have basically an assumption of a spectrum of linear modes, which is not turbulence, but nevertheless tells you something about basic scalings. Okay? So what do we do when we do that? So we get V radial H. This would be the sum over K. Okay. And we would have something like, there would be a minus sign. Now I'm going to get in trouble with all the little signs here. And there'd be something like an I K theta rho S CS. Okay. And there'd be our friend phi hat K squared. And there would be something like omega K, this is continued on the next line, omega star over omega plus, and this is omega K plus I K parallel squared D parallel, right? So this is all one big happy family. That's all there is to it. And you notice, of course, the critical thing is going to be, to getting a contribution from that, okay? And you do a little more algebra, and you can show in the limit of K parallel squared D parallel bigger than omega. So I just dropped that down there to be simple at this stage, just to make my algebra a little bit better. I get V radial times n tilde is, I can write this, or H tilde, it doesn't matter. I can write this as minus a turbulent diffusivity, dt, times dn dr. And this is understood to be n tilde, where dt, right, is equal to the sum upon k of k theta rho s cs CS squared times E phi k over T quantity squared, right, times a factor of k perp squared rho s squared over 1 plus k perp squared rho s squared. This is our friend, the turbulent diffusivity. All right, forgotten, times, not done yet, times 1 over k parallel squared d parallel. Now, let us trace out, so let me, can you guys all see this, or should I rewrite it in the middle? You,
How do we get the velocity?
hmm?
I forgot how to get the velocity.
Oh, the whole, just, hang on, let me rewrite it, because I don't think you can all see it. I can't see it. Very important. This is easier to, oh. So D turbulent, and that's the sum over K. I'm writing out the whole thing now, E phi over T quantity squared, and you asked a good question, we'll come to it, times K perp squared rho s squared over 1 plus K perp squared rho s squared, and then there's this factor of 1 over K parallel squared D parallel. All right, now, question number 1, where does the velocity come from? Okay, well, what is the velocity? Right, you tell me, what's the velocity? It's the E cross B velocity, right? Right, so what's the velocity? So that's, what is it, minus C over B. Radial velocity is E theta, which is C over B grad Y phi, right, or grad theta phi, right? Minus sign there. Right? So one of these phi's in the phi squared comes from that radial velocity. You notice that I can, this is a good question you conveniently asked. What happens if I multiply this by C over B, and then suppose since I put an E phi over T here, then I should have T over E here, and then I have grad theta times E phi over T. All right, well, what does this turn into? I multiply and divide by m, and I have TE over MI, divided by EB over MIC, so that's the ion cyclotron frequency. And then I have a K theta, and then I have an E phi K over T. And this, you will recognize, is just the speed of sound squared divided by omega I, and this is equal to rho s CS. Okay? So generically, you realize this thing is really just a cleverly disguised version of V radial of K quantity squared. Right? That's just the mean, that's just the radial velocity. It's a good thing to remember. This is why we go through this stuff, because you gotta know the basics. All right? Is the V radial is of order, in simple terms, K theta rho s, which is usually of order 1, times the speed of sound, times E phi over T. Right? So again, if you needed a quick estimate, and they ask you what's the typical radial velocity in a drift wave turbulence system, it would be given by the fluctuation level, E phi over T, times the speed of sound. Right? So that's a good practical working man's rule of thumb to keep in your mind. okay? Obviously, another thing in drift wave turbulence that's a good practical rule of thumb is since n tilde over n is always roughly of order e phi over t. I mean, really, of course, n tilde over n is equal to e phi over t plus h, but as we've been saying, h is always less than 1. So at a kind of a quick estimate level, you could take n tilde over n of order e phi over t. Right? So drift wave velocities are typically subsonic, and they're subsonic in the degree that e phi over t is small. At the edge, in L mode, e phi over t starts to approach unity. In other words, usually e phi over t is quite small, a few percent. But at the edge, it can be between 10% and 1. So that means the velocities are getting big. You're producing strong turbulence there. Okay? All right, so back to our friend here. So we see then that this really one of the phi's came from V radial, and the other phi came from the linear response of H, our friend here, right? So that's where this came from. Where did the 1 over k parallel squared d parallel come from? This thing in the denominator, where did this come from? That comes from the linear response of H, right? That ultimately came from here. And I made life easy by saying he's bigger than that, so I'll drop that. By the way, would it make ultimately much of if this is bigger than that, but I don't drop this, would it make much of a difference in the diffusion, in the diffusivity? What would the difference be? The answer, all that would happen is 1 over k parallel squared d parallel would go to k parallel squared d parallel over omega squared plus k parallel squared d parallel quantity squared. So the answer is it wouldn't make much difference at all. Right? And the reason for that is, of course, the diffusivity has to be real. So you have an I here in V radial, and the only other I you have is that. Okay? Where did so this guy comes also from the linear response of H tilde. Where did this thing come from? What is that? What have we spent the first part of today's?
Just the two energy station and energy production.
Well, I mean, this came from omega minus omega star, which is what you're trying to get at, right? This came from omega minus omega star, correctly. Exactly. Right. In other words, this thing ultimately had its origins in this guy over here, right? Okay, so you see all the pieces are reflected in the turbulent diffusivity. This is, the classic quasi-linear estimate of the turbulent diffusivity. Okay? Very fundamental idea. Now, we'll just check the time since I don't have a clock here. We're doing fairly well. Now, let me say,
There's a difference in as case H rho as there's no signal, but
oh, what do you think, you're asking where does the other k theta rho s
Yeah.
come from? It comes from this, right? Because omega k minus omega star goes as, what is it, minus k perp squared rho s squared omega star over 1 plus k perp squared rho s squared. And omega star is equal to, Jean-Lay, k theta rho s cs over L sub n. So that's where it comes from, okay? Now, what's the fundamental idea of a diffusion? So we're writing, by the way, then the flux. The particle flux is just equal, in this thing, is equal to the turbulent diffusivity times dN dr, right? And then if you had any residual collisional diffusion, there would be something like d0 dN dr. We're generally not worrying about that. The neoclassical